So this lecture is going to be on electrostatics, weather, and thunderstorms. That lightning is electrostatics. But we got to understand a little bit about weather, what's going on. So there's no real one way to start or end this, so we'll just go ahead and dig right in. Airflow is associated with pressure. Air always moves from high pressure to low pressure. Air moves outward from high pressure, right? From high to lower surrounding it. And air moves inward towards low pressure. If it's always moving from high to low, there's some really basic rules that apply here. High pressure generally means clear skies, but it can be cold. This does not indicate temperature. It's simply just the pressure of the air. Low pressure, generally cloudy, with precipitation possible. Just because there's low pressure moving through an area does not guarantee that it's getting rain or snow or whatever that precipitation is. There are specific types of frontal boundaries. There's a cold front and there are warm fronts, and these are the two most common. But a cold front is simply saying that colder air is moving into warmer air, and that a warm front is just saying that warmer air is moving into colder air. It doesn't always mean that a warm front always has warm air, though. In the winter, we can have relatively cold air, say teens and 20s, moving into air that's actually 0 degrees. So warm front is relative. It's just warmer air behind the front, and colder is simply saying it's sometimes we could just say cooler. It might only be 2, 3, 4, 5 degrees cooler. So don't get caught up. A cold front doesn't mean cold air always. In the summer, we have cold fronts move through too. A warm front boundary is not an absolute value. It is relative. Air behind the warm front, right back here, is warmer than the air it's colliding with. And it's colliding at this boundary that we call the frontal boundary. So we call the air cooler, not cold. Warm fronts occur in all seasons, so a warm front simply means that warmer air is moving into or colliding with cooler air, period. Warm air moves aggressively or faster than colder air in a warm front condition. The boundary of the collision is the warm front. The warm air ascends, generating a predictable cloud sequence. And we're not going to get into the cloud sequence today. In a cold front, this is when colder air, or cooler air, moves into an area with warmer air. Right? Colder air, it's going to be denser, it's going to stay closer to the ground, it's going to move into warmer air. This is not an absolute value, it's also relative. Cold fronts move through our area during all seasons, like that of warm fronts. But at the cold front are generally more responsible for producing severe weather, including tornadoes, lightning that we'll be studying in our next couple slides, hail, and strong winds. We just have a much greater, let's just say a steeper slope here in which air is pushed to rise vertically. It just moves a lot faster. So it rises up, and when you see this cumulonimbus cloud, generally severe weather is occurring. So how does lightning occur? Well, lightning is an electric current that occurs in electrostatic charges built in clouds. As the ground or land warms, right, from sunlight, it's going to heat up the air directly above it, and this is called conduction. Warm air rises and the water vapor in the air cools and forms a cloud. That's called condensation. As a cloud builds in size, it grows upwards. In the tops of clouds, the air is below freezing and the water droplets turn to ice, right? As air rises in our atmosphere, it gets colder, sometimes cold enough to freeze. As the ice collides with other ice, the charges separate, and this builds up charges in the cloud. We can see that in this picture here. Eventually, the entire cloud builds up electric charge, much like that of you rubbing your socks over carpet, just on a much larger scale. Where, we're talking the difference between your feet versus from thousands to tens of thousands of square miles. That the tops of clouds have a tendency to become positively charged, and whereas the bottoms or the base of the cloud become negatively charged. The charges have become separated from the interactions of ice and water droplets. So when the negatively charged base of the bottom grows large enough, a giant spark or lightning can occur between two charges within the cloud or the ground. Right? So you can have lightning. Most lightning, over 90% of all lightning occurs in clouds. But lightning is a giant electric spark. If lightning strikes the ground, we call it a ground stroke. And notice in this picture, we actually can see charge polarization. The negatively charged base of the cloud is going to repel electrons in the ground, leaving this slight temporarily positive surface. So in summary, ice and water within rising clouds separate charges, leading to a negatively charged cloud base and a positively charged upper cloud. Upper cloud positive, lower cloud or base of the cloud negative. And this is where we can view charge polarization. The negatively charged base repels these electrons. By definition, we could say that this is a balloon sticking to a neutral wall. Same effect. Electrostatic forces, simply we're applying Coulomb's law. Going to repel electrons, it's going to be attracted to the positively charged surface. So you might say, well, why does how do animals know? Well, their fur can actually pick up, it can be like little indicators, little sensors of saying, well, there's some electrostatics in the atmosphere. So they're smart. They run and hide. So what happens in this case? Well, we get lightning. Rising and sinking air masses, along with moving ice and water droplets, build electric charge through friction. Charge is separated at different locations in the cloud. When the charges build enough, grounding takes place. That's what we see when we see a lightning strike. Step leaders reach out and connect positive to negative. We're not getting into what a step leader is. But lightning superheats the surrounding air and causes expansion and contraction of the air molecule, generating thunder. Thunder is the direct result of the superheated lightning heating an air molecule, expanding and contracting it, creating a sound wave, or in this case, a shock wave. So thunder is the result of lightning. In a fraction of a second, lightning heats the air around it to incredible temperatures, as hot as 54,000 degrees Fahrenheit, 30,000 degrees Celsius. That's 5 times hotter than the surface of the sun. The heated air expands explosively, creating a shock wave as the surrounding air is rapidly expanding and then contracting rapidly as it cools. So it happens very, very quickly. So this creates an initial crack sound, followed by rumbles as the air column continues to vibrate. The next time you observe a thunderstorm, do the following. You can actually feel the heat of a lightning bolt, even at distance, on your face from a distance. And secondly, you can count from when you see the lightning to hearing thunder. About every 5 seconds difference from when you see lightning, start counting, and that equates to about 1 mile away to when you hear the thunder. So we can watch a time-lapse video of lightning strike.
Here we have a picture of a ground stroke. We have a step leader. We have this negative charge from the base of the cloud reaching down. It connects or kind of completes itself with a positively charged ground. It gets polarized and it creates or completes the ground stroke. And all of this takes place in well under a second. So this happens within kind of a blink of an eye. We don't see all these details until we time-lapse or slow it down significantly.
So what happens when something gets struck by lightning? Well, if I look at this tree here, lightning superheats up water molecules. And lightning has a very high voltage, which is an electrical potential. When lightning strikes a tree, the sap, which is a poor conductor of heat, heats up very rapidly and it boils, creating an internal vapor pressure that causes the tree, or whatever the object is, to expand and explode. But it's current that kills. Current is what does the damage to humans. So when you look at these pictures, these are called Lichtenberg figures. These are lightning flowers. They are branching features of the body as a result of lightning strike. And the lightning literally travels around your body, around the oils and the water vapor in your body, and it just happened to have a kind of this material on the outside of your skin. It might be on a very, very small level, but it literally just burns this in. This would be a scar that would last a couple years. But lightning doesn't only strike land. Then in the picture here, we get multiple ground strokes of lightning striking Lake Michigan. And this is looking north along Lakeshore Drive.